is the last time we are discussing the Lagrange multiplier. So I think one more notes for the Lagrange, and then we can move on to chapter 15. Okay. So another notes for Lagrange. If having two constraints. Okay, let me just giving you the example, okay, so that you can familiarize on how to use the Lagrange formula. So you have the function of f, and then you have also this and this. So you have two constraints. So this is the first constraint. This is the second constraint. Okay. Now, if you want to use the Lagrange, we can still do this method. The idea is having this Lagrange in two terms of two symbols. So you have the lambda, and then the other one will be this mu. So we will have two Lagrange multipliers here. And what we need to do is still the same as we did before in previous example. So first, we need to find the relations between all these gradient factor, okay, f, g, and h. So we can find the fx, and then find relation to gx, and find relations to mu hx. And the other axis as well. And z. And then the rest is we need to solve all the solutions. So we need to relate all these equations and find how we can solve all the equations. Okay. So this will be 4 and then 2 lambda plus this is just 0 because there is no x in the second constraint. And then for the partial y, we have for f is 6 and then lambda plus 2y mu. Okay. And for the z, this is -2. And then 5 lambda plus 4z. So 4z mu. Okay. Now we have these three equations. Let's start looking at this first one. So the first one is straight up a constant 2. Lambda is 2. So by this information alone, we can exchange all the lambda with 2, right? So this is 6 and then 2 plus 2, right? And then we can solve this and find that y is 2 over mu. Yeah. And then z, from here, we can also change this, and this is it becomes 10, right? And z becomes -3 over mu. Now we have equations for y and for z, right? And if we look at the equation here, the constraint, we can use y and z for this second constraint here, right? Okay. Now we can take this y and z into the equations. We look at this will be resulting 1, or the mu itself it's plus minus 1. So we have two possibility. So first we can look at mu is positive 1. That will be y equal 2 and z will be negative 3. Or mu is negative 1. From here, from both of this, we can take the first constraint and look for x. So 2x plus 2 plus 5 equal 1. So 2x is 14 and x is 7. So that's the first possibility. And the second one is 2x negative 2 plus 5. And 2x is negative 12 and x is negative 6. So we have these two conditions. So we have these two values or two coordinates in terms of the function. So we can try to check these two. This will be the first one resulting in negative 42. The second one is 46. And we can conclude from here alone that this will be the minimum value and this will be the maximum value. So whenever you find x, y, z from the Lagrange, you will find either it will be minimum or maximum or both. You will have you will find two points, okay, directly. Okay, so now you can try to find the Lagrange by if it's having more than one constraint. But I think in this chapter we only have the maximum constraint is 2. So you have the lambda and you have the mu. Okay, so for Lagrange, so whenever you have some value that constrain the function itself, you can always use Lagrange. Okay, you always use the Lagrange. Okay. Okay. Any questions? I think it's not that difficult. I think the concept for Lagrange, the idea is having the gradient factor, okay, and then having the multipliers, which is the Lagrange, okay, the lambda, the mu, and either finding the lambda or just use all the relations you have to find the x, y, and z. Okay, okay, that's it. The chapter 14. So this will be the end of chapter 14. Okay, let me check. Maybe it's some one or two questions to review the chapter 14, but try to check the contents. Okay, maybe the first one is the okay, some examples exercise for chapter 14. So equations of plane to the surface let me rephrase this. This should be fine. Equation of plane to the surface. The surface is cos x, y, z equal x squared y squared plus c at 1, -1, and 0. Yeah, just that. Okay, can you try? Maybe I'm giving you around 3 to 4 minutes to check. And then the second one is let me write this. Recall that you have this relations. So if you have and then you have u, the unit vector is already prepared, 3/5 and 4/5. Calculate. So this means that the second directional derivative, the second directional derivative. The try this too. I'm giving you some times to check. Maybe yeah, maybe it's 5 to 6 minutes. I think you can try the first one. I think it's a lot. It's shorter than the second one. The second one maybe a little bit of calculations. Okay, if you find the answer, you can write the answer on your chat in the chat box. Maybe the first one. I think the first one is not really that complicated. The calculation, I mean. For the second one, I think it has some calculations. Mm-hmm. 2x plus 2y plus c. Okay. I think good. I think still not really correct for the equation plane. Any other answer? But the form is similar, but a little bit different. Z plus, yeah, z plus 2x minus 2y. Yeah, it's correct. It's correct. It's correct. So first, okay, actually what I want to make notes here, okay, basically this is the 14, I think 14 points in 14.6, right? So the tangent plane that you have learned before, actually, if you are looking at the 14.6, you have another form to tell the equation of plane, right? And this form is actually, you can use it for any type of equation of plane in chapter 14, okay? So whenever you find this equation here, okay, first see that it's all having the x, y, z. So we need to make out a functions with three variables x, y, z. So let the or maybe moving around here. Okay. So let's say we have a function of f, and this is the function. Okay. Okay. First, let's take the gradient vector. Let me just write the partial f, partial y, and partial z, and then calculate all with this function of f here. So we will have minus sine. Oh, I am making with comma, sorry. Sine, and then multiply with, or maybe I'm putting to the front here to make it clear. Okay. And then negative 2xy squared, right? And then the partial y will be negative xc. Okay, and then the third one is, so you need to be careful in this. Okay, so to the signs and then how the derivative will be. Okay. But because we have the point is 1, negative 1, and 0, so we can look for z equals 0. So z equals 0 here, it's making all 0, right? So we only having this 2. So negative 1 still positive. So this will be resulting in negative 2. And here is 0. And we have this is negative 2, but we have negative 1, so it's positive 2. Here is 0 here, right, for z, and this will be all 0, and we have negative 1. So this is our point, right? So we can write the gradient vector for the point 1, -1, and 0 will be -2, 2, and sorry, -1. So we can use this to our equation of plane. So -2, and then x minus x0. The x0 is 1, and then plus 2, and then -1, and just see, because it's the 0 is 0. And we can solve this, and we can find that c is equal this, or you may write in this term. Okay, both are correct. Okay. Okay. Now the second questions. The second directional derivatives. This is, I want to just to review what we have done um, in all the chapter for directional derivative. Okay. So first is let me write the directional derivative is the gradient vector dot product with the let's say u. Okay. And the gradient factor, let me write the gradient factor here, is partial x and partial y, because we only have two variables. Okay, so partial x will be 3x squared plus 10xy, and then partial y will be 5x squared plus 3y squared. Okay. Okay. This method to find the secondary directional derivative, there are two ways. You can find the dot product first, and then you derive one more time, or you can try to look for the relations for the second directional derivative. So, for example, um, let me write the directional derivative again here. This will be partial x, partial y, and let this u become just ab. Okay, to see how the forms looks like, and this will be dot with the a and b. Okay, or we can write this partial x a plus partial y b. Okay, this is similar to what we have done in proving on the determinant on the maximum minimum value. So by second derivative, so we are going to take derivative derivative partial x, right, of the partial x a plus partial y b, and it's still a, right, because it's directional derivative, so you need to still have a. So actually this is, if you think this is the partial x, right, so it's partial x, first is partial x x and partial x y. Okay, I hope you get the point. And the other one will be the partial y, and this is the the function. Okay, and now we can write down all the second partials. So partial x, for partial x, it's become partial x, and then a squared, okay? And then plus partial x, y, and then let's say ba, and then plus partial y, x, and then ab. But because it's the same xy and yx, later we can plus both of them, and partial y b squared. Okay. And now you have partial x a squared plus partial xy 2 partial xy ab plus partial y b squared. And this is, you can use this information into most of all the second partial problem. Okay. And now we can exchange all the informations. Okay. So maybe I'm writing here. So f for partial x, we have 6x plus 10y, and then partial xy is 10x, right? And the partial y is 6y. And we can use these three informations to our equation here. So partial x is 6x plus 10y. And then a is 3/5, and then squared 9/25 plus 2, and then xy is 10x. So it will be 20x. And then multiply with AB is 3 and 4, so it's 12. So 12. Okay, and then the last one will be 6y. And this will be 16/25. And then we need to use the coordinate. The coordinate that we are going to observe is 2, 1, right? So we change all terms. This is 22. This is 40. And this is 6 and 16/25. A little bit calculations, you will get the answer is 774/25. Okay, so this is the formulation for the partial, the second partial that you can take, and you can also use that if you have another second directional derivative. Okay, and that's just additional notes for the chapter 14. Okay, good news for today. I will only give you the chapter 15, okay, for now. So it will be chapter 15. Yes, Doran? Yeah, what you want to ask? Effectiveness. It depends on your preference, but my preference is using this this formula here, because when you are dealing with so if you are dealing with this at the very beginning, sometimes you take some miscalculation from here, and then the rest will be you are going the wrong way. But if you take from here, it will, in my case, it will minimize your miscalculations. But that's just my opinion. Okay. Okay. So chapter 15. This is multiple integrals. Okay, so now we already have, today is June 7, right? So we still have, chapter 15 is really long. So we still have a long way in chapter 15. So probably some parts I will maybe a little bit skip, okay, and have you to check by yourself, okay. And I think most of them are about the trivial things in chapter 15 that I think not really necessary. So I will just go through what is necessary in the multiple integrals. Okay. And we only have time until June, around June 20 or 21, right? This is already final exam begin, right? So this week we will not have any more course, so we still have around more or less, we're only having 2 weeks, right? So I hope I can make it. So if we need more time, because I believe next week is holiday, right? So we may have additional class, okay, to take, but I need to ask from you maybe later. But at least 2 weeks we only have time for chapter 15. But let me just going through what we are going to overcome in the chapter 15. So basically, we are basically solving integrals. Okay, if you remember integrals from calculus 1, the definite integral is basically, the definition is came from the limit. Sorry, of the we already discussed the Riemann sum, right? So this is the Riemann sum, in which it's actually, if you draw a graph, it's actually the rectangle, the small rectangle that that are covering the area under the curve, right? So let's say it's from A and to B, and what you need to do is you plus all, or you add all this rectangle here. So there's a lot of rectangle from A to B, and the rectangle is this formula, and you add all those formula. And when you cut the rectangle into much more pieces, and then imagine the rectangle becomes, the cutting becomes really or approaching infinity, and in that way we can define our integrations. Okay, so in calculus 1, this is all about area, right? Area under the curve. Now in calculus 2, we are calculating the volume. Instead of area, we're calculating volume. Let me just give you a brief example or brief intro. So let me draw the, let's this let z is equal the function of the two variables x, y. Okay. And in XY plane, we have a region that are defined as R. Okay. Let me write some notes here. So given a function of two variables that is continuous and non-negative on a R region, this is on XY plane. So I need to find the find volume of solid enclosed between surface Z and XY plane. Okay. So what the sentence mean is this is a surface C, okay, and this is the region R on the XY plane. So this is XY plane. So Z, X, Y. So what we are going to do first is we are going to mapping the region R to the surface C. So so let's make a cut and make it a square. Okay, and then imagine this square will be mapped through, let's take this first. And then mapping this region to the surface. Okay. So this is mapping R to Z, okay? Now we have this a solid, right? This is a solid. It's the volume of, if you remember, this is parallel pipe in factors. If you remember, the volume, of course, is just area, and then multiply with the height, right? Or area of the rectangle, right? And the height will be the surface of Z, right? Or if we can take some simplifications, this will be the delta, and then the Z is a function of X and Y, right? This means the small area here, okay? The square, I mean, okay? Now, if you look more closely, let me take some new slides, okay? Is this okay? Okay, this is what we are going to approach. Okay, so we are mapping the R. Okay. Oh yeah, it should be having not only xi but xij, because we have I and j two parts, right? And when we are going to take all the squares and mapping all the squares into the surface, we will have this kind of volume, right? And you can notice that there will be some difference here, right? A little bit difference, and in our observation, that will be the error, right? So the more clean, the more smooth the surface will be, then the volume is more likely to be an exact solution, right? If you want to take the volumes. So so volume is actually, or it's approaching from here. So this will be okay. So this will be the Z, and this will be the area, right? And from here, we can take the definitions, or maybe let me write some notes here. If f has both positive and negative values, then the volume is the difference between R and surface below and above xy plane. Okay, this is just an additional notes. Back to here. From here, the volume is, we can have definitions. If the z, or the functions, is positive, then volume of solids that lies above the rectangle R and below the surface C is, now we have definitions that, using this, the same limit definition as in calculus 1. Oh, sorry, this should be different. Sorry. Should be maybe different number to make it clear. So this will be m, and then n is going to the infinity. Okay, now the definitions will be, or maybe going to the right, here. This is this, or maybe we just going here. This is the same as the double integral on the region of R of the function of two variables, and then this will be dA. And dA depends on which term you are preferring. It could be dy dx, it could be dx dy. Okay. Okay, now you have these expressions, and there is an example on how to use these expressions on the Riemann square. But I think I will skip that because that not really that important. Let's just evaluate some example from for double integral. So maybe here evaluating double integral. Let's say we have a function, and this is a, b, and then c, d. What this means is this is actually, I'm using another bracket here, or maybe using different color. So what these double integrals means when you evaluate as in the calculations, this one you need to integrate first, right? So integrate the integrals that are inside. Okay? Examples. Okay, example. Let me give you the simple example, so that you can have more of familiarized with the double integral. So this means you are integrating the inside first. Okay, integrate this with respect to y. So y becomes half and y squared, right? So this will be x squared y squared over 2 from 1 from y equal 1 to y equal 2, and then dx. Or maybe the x will be black here. Okay. And now we integrate with respect to x. Or maybe we calculate the inside first. So 4 minus 1 is 3. So it will be 3 over 2 x squared and then the x. And this is divided by 3. It's half x cubed from 0 to 3. Or we can calculate, and this is 27 over 2. Okay, that's the idea. But anyone want to ask? Dora, you want to ask? No? Because you raise your hand. Do you want to ask something? Oh, okay. Okay. So how if we change the order? So for example, this is from 1 to 0, 3, still the same, and then the x dy. So you see, this is the similar equation, but we are exchanging this dy dx and these integrations. Okay. So if we change the order, then we are integrating the inside and then the outside, right? So integrating the inside, we have and this will be 27 over 6 and then y squared. So look at the results here. It's 27 over 2. It's 27 over 2, right? So it tells you that when you change the x dy, still the results will be the same. And that is our another theorem. It's called the Fubini theorem. So let the R be a rectangular regions defined by and if functions continues on this rectangle, then okay, that's the Fubini theorem. Okay. So I'm skipping some parts, like the introductions. If you look at your textbook, they have some Riemann sum similar to your calculus one, like midpoint rule and some other example, but I'm skipping them. So we directly go to Fubini theorem. And then directly go to, probably before going further, let me just make some property for all these integrations. So property, if you have a constant, this is a constant, so C is constant. This is plus or minus. You have another functions, dA, and this will be equal to maybe plus or minus. Okay. The third one, you can separate the area. Separate the R, right? The region. R is R1 plus R2. And the last part is you can have two functions inside. One is function of x, one is function of y. You are sure that you know that there are two different functions, and you can separate those functions and make out this a, b, and c, d with respect to each axis. Okay, this is some important property in the double integral. Okay, from here, actually number 3 and 4, I think it's kind of essentials in the double integral. The number 1 and 2, I think in the general integral in the calculus 1, we already have this kind of property, right? Or let me add R is meaning R is the square of the AB multiplied by with CD, right? The interval from A to B multiplied from the interval from C to D. This is just to emphasize the rectangles. The next part is the average value. Of course, you already have learned in calculus 1 before. The difference in calculus 2, the average is now you are using the area, okay, instead of the x. This A is area of R. And we can also write this if the functions are positive. Okay. I think not much of discussion from this average value. And I think that's just the introductions, on how we are going to have the double integrals. Okay. Okay, so the next part is 15.2. Okay, we still have time. Actually, we don't really have quiz for today, and the quiz will be next Wednesday. And I will check your exercise whether you can solve some exercise or not. I haven't checked yet, all of you. So we are continue until the end of today's lecture. So 15.2 is it's called the double integrals over general regions. Okay, now general regions means the R, okay, the R that we are make before. Actually, the previous case here, it should be the square, okay. It should be square. So I think I make some mistake here. I'm skipping to the general region. So this should be a perfect square like that. Okay. And now we are actually going for the general regions. Okay. So it's not the exact rectangle. So if we take the xy plane, and let's say we have D, right? And then we have let's say I'm going to copy all of this. Copy. Okay. And then I have another, let's say R. This is R. Suppose D is a bounded region. So D can be enclosed with, I think I will erase this because maybe it will confuse you. Can be enclosed within the R, the rectangular R. So we need to define a new function. Let's say the big F, okay, the big F with domain R. Okay, this is the new function. And what we are going to define is this, the big F will be the same with the equal with this small f if the x and y is in D, and it will be equal to 0 if is in R but not in D. Okay, and practically what we are going to look for in terms of the surface. So if this is the surface of Z, And let's say this is our graph here. We will have a projections of surface in maybe a projections. Okay, I hope you get it. Okay, I hope you get it. It's actually what does it say is this big function f is just equal this small f. Okay, it means the projection of the surface will be the same as the the small f. So what does it mean is it's actually the same calculation as we did previously. Okay, and now the region here have two types. The first one is okay, this is just illustrations. So you have the function of x. And, I name the functions as g. Okay, so this is type 1. And another is type 2. This is c, d. So x is function of y. And let me name the function h. This is type 2. The difference on this type is just the difference on how we integrate the results of the functions. So the double integral is still the same general equations. But here, one term is a constant. The x is a constant, a and b, while the other is a functions. Okay, let me move this to right side to make it more clear. So this is type 1. Okay, so this is actually what I'm doing here is a summary of your textbook. Okay, there are a lot of text and examples, but I think I'm just writing down the essential parts on your chapter 15.2. And type 2 will be, let me write the general equations. It's the same as previous. And now we are going to use the y as a constant. So c, d, and then the x, dy. Practically speaking, both of this type, it depends on what calculation we are going to look for, or what questions we have. If we can define the functions in terms of x or in terms of y, then we can choose whichever method that we are going to do. Okay. So let me give you an example. Yeah, maybe one or two examples. So example, calculate these integrations, and D is bounded by now you have the area that is bounded. So meaning on the xy plane, we will have our set of bounds. Okay. And usually in the multiple integrals, we don't really need to draw the volume. We only need to draw the area. Okay? Because if you see here, we need to know this bounds, right? We need to know what kind of bounds that the area have, right? Because we are not really sure what is this this bound here, right? The functions can be any functions. It can be a quadratic surface. It can be like paraboloid, etc. Or it can be just a plane, right? But we need to know what's the boundary of the plane that we are going to evaluate, right? So what we are going to do is, and I'm suggesting to you, if you can draw the area, I'll draw the area first. We only having these two, right? Meaning it's just parabola, right? The first parabola is just 2x squared. Okay, probably that is our parabola. The second one is parabola, but it's 1 plus x squared. So at zero is y is equal 1. Maybe here. So maybe around. Yeah, more or less we have these two parabola. The area D is bounded by these two. So this is the area of D. It looks like we are solving similar to what we have done in calculus 1, finding the area, right? But later, what we need to do is we need to justify this area and then take the area to these equations here. So what the first thing we are going to do is finding this intersection here, okay? And we are going to do that to find the x. So x squared is 1, or it's plus and minus 1, right? So we have x is negative 1 and x is 1. Okay, now we can take that information into our double integrals. So this is x plus 2y. Okay, let me write that. And then takes this constant as the outer integral like that. So we will have dy and dx. And takes the equations, these two equations here, as our y. Okay. You will notice that why we need to take this constant here is because this constant will be the last thing that we need to formulate. And this here, what we are going to do, or not there, maybe here, this dy here, is we are going to replace all y with x. So at the end of the day, you can have a finite number that you can really calculate, right? Okay, so first, let's take this inside first. Let's take the integral from the inside. So it will be xy and then y squared, xy plus y squared. You integrate, and then you need to plug in 1 plus x squared and 2x squared. And you still have another integral outside that is with respect to dx. And we need to take the informations inside. So x and then 1 plus x squared. And maybe writing the here. And then plus. It takes some time to deal with this. Or yeah, dx at the end. Okay. And you will get yeah, it takes sometimes to check all the then plug in -1 to 1. Yeah, it takes sometimes to calculate. Okay, that's the first case. Okay. Okay. Maybe one more example. Okay, let me just write find volume of solid that lies under z equal xy above D. And D is region bounded by y equal x minus 1 and y squared equal to x plus 6. Okay, if you want to compute, you can compute this. Let me give you the what the area will looks like. So x minus 1, I think this, yeah, this will be the area. Now, before we go into to calculate, let's just look at the formula here. Now you have y squared equal to x plus 6. This will be a side parabola like this, right? So in order to make the necessary calculations, okay, you can take some, for example, if you look at this two equation here, if you want to find the intersection, it's easier to take the equal for x, right? So x is equal y plus 1, and this x is and you can take these two equals, right? So I will write in terms of x y plus 1. I think this is much better, right? Instead of using y like in our calculation here, right? So we can take this x equal y plus 1. And let's imagine we'll be having sorry, I just make parabola here. Okay, let's imagine this is the parabola that we are going to evaluate. And the d is inside. So we need to find the point here and here, the intersection point. So let's do that. So y plus 1 is equal. So we can solve this and solve through the quadratic functions. So we will have y equal 4 and y equal negative 2. So this will be 4. And this will be negative 2. I think that's a good proportion. So this is negative 1 and 2. Yeah. And from here, we can take the integrations d xy dA. So d, we can take xy and take the y first. And then the second one is the x. Now, which one is the top one? So if you can look at this graph, so similar to what you have done in calculus 1, the top one is x, right? The right one, right? The red one is the below. If you look at if you turn and rotate the graph, right? So this will be y plus 1 is here, and this is the below, right? The boundary below, and then dx dy. Okay, and I think you can use this same exact way like this one. You integrate the first is the inside integrations, and then the outside integration, and put in the value. Okay, so I will not calculate. You can calculate by yourself, I hope. This will be resulting 36, okay? If I'm not mistaken. You can check. So necessary skills in this part of lecture. First is to draw the region to see which one is the top boundary, lower boundary, right? And then necessary, you need to reverse order if necessary. So dx dy. So you need to choose which one is a better approach to calculate the double integral. Okay. And usually you can see from the boundary that the area will be. Like from here, probably at the very beginning, you look at the boundary and you think that, okay, maybe we have y equal x minus 1. So maybe we have x minus 1 as our boundary. But then the second one, you are looking at y squared. So it's better to have x, right, as your functions. So that's the skills that you might need to draw the region and reverse order if necessary. I will add some notes, okay? So probably from the very beginning of the chapter 15, when I'm introducing you to double integral, because I've said that this is actually related to volume, right? This is functions. So probably this is what you will get. But actually, you can also use the double integral to find also the area. In some cases, you can use that also. So area as double integral. This is just additional notes. So what we are doing here is actually if this is the surface and this is the projection, and let's say this is having z equal 1, okay, and then we have a boundary like that. So volume is area multiplied by the height, but because the height is just a constant one, so volume is equal to area. So this is a special case that might happen, and you can actually using it to find the area instead of volume. So we are just taking one here, and practically in practical, if you have, like, for example, dx dy, then this is just integrating to x, and it will become x, right? X dy, and you need to evaluate this. So this is some special cases that might happen. If you need to calculate the area of region using double integral. Okay. Okay. So you have 15.1, 15.2. I will review again next Wednesday if we have time for this 15.2. But actually, we can move on to 15.3. Okay, 15.3. I will just giving you the brief intro of 15.3. So this is double integrals in polar. Okay. As a little bit review in the previous chapter 10, right? You have at least this formula to convert the rectangular coordinates to polar, right? Or from polar to rectangular. And the R will be, if we have the unit R, okay, and then this is 1, 1, 1, 1. Now, to make it more a little bit complex here, if we draw these 3 dimensions to give you an idea. Okay. So let's imagine this z now is a function of r and theta, not in x and y, but in r and theta. And we have okay, we have this polar approach here. So let's say this is the theta equal alpha until the last theta here, theta equal beta. Okay, and this is will be our region to look for, or region to be as our observations. So if we want to find the volume, okay, if we want to find the volume, we have limit let's just let me use the same same rectangular as in your textbook. Okay. So limit, let's say the mn, and we have m, and we have n. So we have I and j in our term here. This will be, so it's from xy. So x is arc cosine. And the theta will be j. And then delta A. And let's exchange this f with other function that represent polar. And in the delta, this will be delta delta r delta theta. This is from, if you look at here, imagine this is if this is the alpha and this is beta. Imagine that you have two different functions here with different radius. The area means the large sector minus the small sector. So this will be our delta A. And the delta of theta is just beta minus alpha. And the area, the sector, is half r squared theta. I think I will continue this on Wednesday. So I will stop here for the polar. Okay, I will just review a little bit next Wednesday. Okay. Yeah. So actually, the multiple integral, you know what? We still have until, so this is 15.3, right? We still have until 15.9. So I will skip some parts in the middle. Okay, maybe 2 sections I will skip that is not really that essentials for you. Okay, so we stop here at the 15.3. The integrals or multiple integrals in or double integrals in polar coordinates. Okay, so see you on the Wednesday, and because today we don't have quiz, so we will have the quiz on Wednesday, and the topics is the chapter 14. Okay. 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 One more thing. Okay, one more thing, because I've mentioned about the final exam. Probably the final exam, it is maybe on June 25, because I still don't get a schedule from the other courses. Or if you have schedule, like if you have the fixed schedule from other course, you can tell me, and we can set which time we are going to have the final exam. Or if all the weekdays are full, then maybe on Saturday, probably. Okay, but it's up to you. So Friday or Saturday. But let me just ask you again later on the Google Classroom. I will ask you which time you have, or which time you are more preferable. I will maybe make a survey out of the students. Okay. And because we are doing all exam online, so I hope it will be easy to schedule our exam, okay, for final exam. Okay, I think that's it for today. If you have any questions, you can ask, but I will stop the recording now.